Commercial air travel is old enough to have a history, yet imagine. Just 41 years ago, Henry Ford introduced the first all-metal aircraft, his trimotor, capable of cruising with 14 passengers at a breathtaking 100 miles an hour. By the early 1930s, the Curtiss Condor, last of the biplane era, was making scheduled transcontinental runs. Stewardesses had already learned to smile away the discomforts of cramped legs and tired bodies. After World War II, 4-engine airliners dominated the skies, lifting up to 100 passengers across continents and oceans. Now, hardly 2 decades later, the luxury of jet travel puts Paris only a coffee break from London and San Francisco but dinner and a full-length color feature from New York. The next chapter in the brief history of commercial flight will be the new supersonic transport. Our story today on Science Reporter. Hello, I'm John Fitch, MIT Science Reporter. Today, we're at NASA's Ames Research Center near San Francisco, California, to learn about the next generation of commercial aircraft, the supersonic transport. 20 years ago, knowledgeable men were seriously wondering whether man could ever fly faster than the speed of sound. Debate ceased abruptly on October 17, 1947, when Captain Charles Yeager piloted his research craft, the X-1, through the sound barrier, thus marking the beginning of a new epoch in powered flight. Today, manned supersonic flight is commonplace. Military aircraft such as the versatile F-111, the giant B-58, or the mysterious YF-12A, to name only a few, normally cruise at speeds well over the speed of sound. And the experimental X-15 has briefly pushed even beyond the 4,000-mile-an-hour mark. But military and experimental design objectives are basically simpler than commercial objectives. Performance and mission accomplishment are their key yardsticks. Cost is secondary. Commercial airlines, on the other hand, naturally look first to questions of operating efficiency and cost. A supersonic transport must cost no more to operate per passenger mile than do today's subsonic jets. A transport must be durable, able to withstand continuous use for up to 15 years, and it cannot itself cost too much, nor can it require major alterations in existing airport facilities. Another factor of concern to SST planners is the sonic boom. Populations near airports and on flight paths are certain to protest a constant bombardment by shock waves. The British and the French were the first to commit themselves publicly to building a commercial supersonic transport, the jointly developed Concorde. The Concorde, scheduled to begin test flying in about 2.5 years and be in service by early 1971, is a fixed delta-wing craft designed to fly with 136 passengers at speeds somewhat over Mach 2, twice the speed of sound, or roughly 1,400 miles per hour. It has long been known that Russia also plans to develop an SST, and this model, unveiled at the 1965 Paris Air Show, provided Westerners with their first official glimpse of the Soviets' Tu-144. In 1963, President Kennedy announced that America would leapfrog the competition and develop her own larger, faster SST designed to carry 200 passengers at 3 times the speed of sound. Many tried methods of aircraft construction have had to be scrapped for the American SST. In the first place, aluminum, which is what most planes, including the Concorde, are made of, won't stand the heat created by friction with the air at speeds much over Mach 2. A sustained 630 degrees Fahrenheit is routine for a plane cruising at Mach 3. So hot, you could grill a side of beef on the leading edge of the wing. To meet the U.S. goals, aluminum had to be replaced by a totally new structural material. Finally, a lightweight titanium alloy with a melting point of 3,000 degrees Fahrenheit was selected. Having picked their material, engineers then could concentrate on a second major problem, aerodynamic design. Wind tunnel tests like this show that aircraft traveling faster than sound run into 2 types of drag. In addition to the normal drag of airflow over its surfaces, the plane compresses walls of dead air, shock waves, in front of its surfaces. These shock waves can be observed and studied through a special optical system. In supersonic wind tunnels such as this one, engineers have found that a sleek and piercing design is most efficient. The fuselage must be long and pointed, the wings must be swept and flat like cutting edges. Finally, designers had to cope with a third major component of aircraft design, the engine. A new breed of jet engine had to be developed that would push out a little air at extremely high velocities rather than a lot of air at lower velocities. Using the basic research information from NASA's Ames and Langley Research Centers, two aircraft companies undertook the design of an SST. These radically different-looking aircraft are the results of their work. Here in Ames' 40 by 80-foot subsonic wind tunnel, the biggest in the world, large-scale models of these two configurations are being tested for their aerodynamic characteristics at slow speeds. To learn more about these SSTs, we talked to Mr. Mark Kelly, Chief of Ames' Large-Scale Aerodynamics Branch.
These airplanes are designed to cruise at nearly 2,000 miles an hour, which is more than 3 times as fast as our current subsonic jet transports.
Well, how's that going to affect the time, say, to go from New York to Los Angeles?
Well, you should be able to get from New York to Los Angeles in less than 2 hours. That's less than the time difference between the two cities.
You mean you could actually land before you take off, according to the clock?
That's right.
How many people will ride in one of these?
Between 200 and 250, depending on the mix between tourist and first class.
So we still have the 3 and 3 and 2 and 2.
Yes.
Seating on. 200 to 250 people means this is going to be a big plane as well as a fast one.
That's right. It will weigh about 500,000 pounds compared to our heaviest present jets are around 325,000 pounds.
How long will it be?
About 270 feet, nearly as long as a football field. Our present jets are about 150 feet long.
Well, since this is a supersonic airplane, why is it that you're testing it here in a subsonic wind tunnel?
Well, this is because no one wants to land at supersonic speeds. And in fact, the landing and takeoff requirements for the supersonic transport are quite stringent. It must have comparable safety, the same as the subsonic jets, and actually is required to make less noise than the subsonic jets. Specifically, our design objectives are to be capable of taking off out of a 10,500-foot runway on a hot day with an engine failed.
Really?
And the maximum takeoff speed is to be limited to 160 knots. The maximum approach speed is limited to 135. These conditions represent a pretty significant design problem for the supersonic transport.
Well, how are you planning to solve these problems?
Well, I can show this best by looking at the models that we have of the two different approaches to the supersonic transport. Well, this is a 1/5 scale model of the Boeing supersonic transport design. The pilots would sit up in this area. During landing and takeoff operations, the forward portion of the nose is moved downward to improve visibility during landing and takeoff. For cruise, it's up in position as shown here, and the pilots see out of these side windows. Now, the big feature of this airplane, of course, is the variable sweep wing, which we can show back here. This is the same principle that is used on the TFX fighter.
Oh, I see.
Now, the wing is shown here in its swept back position for supersonic cruise. This is approximately 70 degrees of sweep of the leading edge. There is a pivot in the wing in this general area, which allows us to unsweep the wing to approximately 20 degrees of sweep for landing and takeoff operations. This allows us to generate the high lifts required to slow the airplane down. We can show you the wing configuration for landing and takeoff on the other side.
Getting a little old for this.
Yeah. Well, this is the way the wing looks during landing and takeoff operations. You'll notice, in addition to having the wing unswept, we have put leading edge slats on the forward portion of the wing. The purpose of the slats is to maintain a uniform flow over the upper surface of the wing. We also have trailing edge flaps on the aft portion. And these deflect the air downwards over the aft portion of the wing to generate as much lift as possible.
Now, why is it that you want all this extra lift during landing and takeoff?
This lift is required in order to meet the contract objectives of maintaining the takeoff distance less than 10,500 feet and maintaining the takeoff speed less than 160 knots. And we want to do this with as small a wing as possible.
Well, you mentioned a third objective, that is not to have the noise be any louder than with ordinary planes.
This is correct. And one way this is accomplished is through the use of larger engines, which we see here on this design. These engines have over 2.5 times the thrust of the subsonic jets. The airplane, therefore, can climb at much higher angles and will be further away from the community. This reduces the noise that the community receives.
Right.
Now, we can take a look at the Lockheed model and see how another contractor has approached the same problem with a completely different design.
Right.
This is a quarter-scale model of the double delta fixed geometry supersonic transport configuration. Again, the pilots sit up in this area of the fuselage, and the nose droops away for improved visibility during landing and takeoff operations.
What do you mean by a double delta?
Well, the wing, Schoenbach, is comprised of two delta or triangular-shaped portions. This forward delta and the main aft delta shown here.
Well, now, if this doesn't change position, how do you get the extra lift that you need for this takeoff and landing problem?
This is obtained in a combination of three ways. First, this forward delta is used to generate a high-energy vortex.
So like a hurricane?
That's right, which generates a low-pressure field over the aft main wing.
Mm-hmm.
Then the wing itself is much larger than on the variable sweep airplane. And finally, we rotate the airplane to higher angles to generate
tilt it up.
That's right, to a higher angle. When we do this, we lower these leading edge flaps to maintain smooth airflow over the upper surface of the wing.
I noticed that this plane doesn't have a horizontal tail like most airplanes that I'm familiar with.
Well, that's correct, and the tail is replaced by control surfaces here on the aft portion of the wing, all the way across the aft span. These are moved up and down to make the airplane go up and down, or one up and the other down on the opposing wing to roll the airplane.
Oh, and these are the engines under the wing?
That's right.
They're about the same as the
about the
plane
same
on the
thrust
airplane?
as the other.
Well, tell me, Mr. Kelly, have both these planes met these design objectives that you've been talking about?
They have come very close to meeting the design objectives, and I believe that with continued development effort, they will meet the design objectives at the end of the...
more work to do, right?
That's right.
Well, assuming they do, what will happen next?
Well, the next step will be an evaluation of the two designs by a government evaluation team with a recommendation as to which airplane should be taken into flight test development. Mm-hmm. There are people who recommend that the competition be maintained on both aircraft through a flight test stage.
Well, thank you very much, Mr. Kelly. In addition to static tests in a wind tunnel, some of the dynamic aspects of SST performance can best be tested in actual flight by modifying an existing aircraft to reflect various design ideas. Here at Ames, engineers have taken this F-5D, for example, and changed the shape of its wing to resemble that of a delta-wing supersonic transport. Thus, they can test the lift characteristics at low speeds of this proposed SST design. The F-5D has a 5-year history of flight testing various design ideas. Here it flies missions in the critical region of subsonic flight, testing the low-speed lift and stability characteristics of this particular wing shape. Even at these subsonic speeds, the wing edge condenses moisture in the air that crosses it. The resulting vapor creates visible patterns of the vortices which are produced and which provide even more than the expected lift at slow speeds. A
America's newest research craft, the controversial XB-70, has pioneered in high-speed test missions. 2 years ago, it was to go into production as the most up-to-date member in our arsenal of long-range bombers. Once Congress canceled the bomber program, NASA and the Air Force agreed to use the two prototypes jointly as test craft. Although because the XB-70 is expensive to build and operate and has only limited payload capacity, it can never be used for commercial travel. Flying 3 times the speed of sound at 70,000 feet, about the same speed and altitude the SST will cruise at, this huge white bird now gathers invaluable data on stability and control characteristics. At the same time, cruise missions check out engineering solutions to the most difficult problem of high-speed flight, sustained heat. Hydraulic systems, electrical wiring, bearings, and seals have all been redesigned to withstand the scorching temperatures. Tests also gauge airframe strains and fatigue under these extraordinarily demanding flight conditions. As the only large experimental aircraft able to cruise at Mach 3, the XB-70 has a busy schedule, and much of the information gained on these flights will be directly applicable to the SST. This plane, now coming in for a landing, has a long history of contributions to in-flight research. It's a Boeing 707 prototype. In fact, the first 707 ever built. In its day, it held the transcontinental speed record. But much of its long life has been spent playing charades. After flying countless missions for 707 testing, engineers, with a wave of their wand, miraculously turned it into a 727. Now, here along the coast of Virginia, where NASA is testing the handling and maneuverability of the two supersonic configurations, it pretends to be an SST. To learn more about this versatile plane and the tests it's performing, we talked to Mr. Robert Shade, project manager for SSTs at Langley Research Center.
Mr. Shade, that was a beautiful landing. How are you?
Thank you.
What is the purpose of this rather unusual-looking airplane?
Well, the purpose is to simulate supersonic transports during the landing approach with a large subsonic jet transport.
Well, now, how can you do that? I mean, this is a subsonic transport. It looks very much like a 707.
Well, it looks like one, but it doesn't fly like one. We have inside the aircraft a computing system that takes all of the aircraft's inputs, like the pilot's control and the movements of the aircraft, into the computer. The computer analysis of the thing tells the controls what to do to make the airplane fly, just like a supersonic transport.
I see. So there's a computer between the pilot and what actually happens.
That's right.
So that if he pushes some normal control, it doesn't respond just the way he might expect it to.
For example, if he pulls the control column back halfway, the normal airplane you see there would pitch up rather rapidly.
Yeah.
But after it goes through the computer takes some of this out, so it pitches up a lot more slowly, like a real large supersonic transport would.
Which couldn't possibly respond as fast as a slower
correct.
plane. What is the inside that nose that sticks out like a beak?
Well, that big boom you see back there is our angle of attack, which is for the airplane going up and down, and angle of side slip indications.
Mm-hmm.
And when this aircraft moves either up or down or back and forth, this little vein right on the very tip end of this boom transmits signals back to the computer, and then the computer takes these signals and uses them for the simulation.
I see. That really tells you what the plane is doing.
That's correct.
But if the pilot can see out the window, I think that would tend to spoil the effect. I mean, does it really feel like he's flying at supersonic speed?
The only thing that he does not feel is that the pilot is closer to the center of gravity of the airplane. He's not quite as far out in the front. Otherwise, the airplane motions, the movements he goes through, and most of the visual cues he has are essentially the same.
What kind of men do you use for flying this? Or regular pilots? Or?
Well, we have been using 2 of our NASA research pilots to conduct this low-speed landing approach evaluation, and right at the present moment, we're using 4 outside pilots to evaluate it to get a more comprehensive indication of what we have done.
What's their reaction to this peculiar interference with their normal controls?
Well, most of these people that are flying it are pretty well versed in terms of test pilots, and they're used to this sort of thing, and they can sort out the good and bad things and tell us what we have here in the way of a supersonic transport.
Well, now, can you try different designs, sort of program them into the computer? So
Definitely.
It isn't just any supersonic transport.
We have a big patch board, it's about this square, that's just covered with wires. We call these computer patch boards, and when we fly a given configuration, the patch board is pushed in to the computer, and this computer then responds to this particular configuration. If you want to change from a variable sweep SST or supersonic transport to a delta configuration, you just take the patch board out and put another patch board back in, and then the airplane flies like the other configuration.
Is it too early yet to say which designs look promising?
Well, all I can say is they all fly.
They all fly. Is part of the purpose of this to see whether pilots can actually handle these airplanes?
This is the biggest thing we're after. We don't know for sure until the actual airplane is built whether the supersonic transports will fly like we think they will.
Mm-hmm.
And this is just the next step we're trying to do here to get a better feel for what the SSTs will be doing when they fly.
Not all SST testing is best done in the wind tunnel or in the air. Often engineers want to try out a whole variety of conditions, including some that might prove unsafe in flight. To see how these tests are conducted, we talked with Mr. Seth Anderson, chief of the Flight and Simulation Branch here at Ames.
As you can imagine, it's rather expensive to operate a large jet transport. For that reason, we do quite a bit of our work with ground-based simulators. In this way, we can cover a broad range of parameters and then use the flight test results to validate the ground-based results. We have one of the simulators here.
Oh, is this a supersonic transport?
It's a cab that's used to represent some of the supersonic transport's characteristics. This cab can actually move. It rolls plus or minus 12 degrees, pitches up and down, and moves through an altitude range of about 3 feet. This gives a pilot a lot more realism, a much better feel of actually flying an airplane than if he were standing still.
So he's flying by the seat of his pants.
That's correct.
Now, what does he see? A movie of a typical flight path on the screen?
No, it's not a movie, John. It's a projection of a landing that's given by the projectors on top of the cab through a closed-circuit TV system.
Television.
And it's actually in color to add more realism again. And this equipment is in another room. And the camera is driven over a landscape to show his approach to his landing and to the actual touchdown on the runway.
When he moves the control in the cab, does that sort of move the camera over the landscape?
Well, not directly. We do have to go through a computer setup to give the actual supersonic transport's characteristics.
Oh, I see. So when he moves the control, it may not respond instantaneously. It responds more like a big sluggish airplane.
That is correct.
Could we see this in operation?
Why don't we take a ride?
Okay. Why don't you go first here?
As you can see, this is the most important part of the cab, only where the crew is actually operating. Why don't you sit in the co-pilot seat, and we'll have a preview of an SST aircraft making a landing.
I've never even had a chance to do this in a regular plane. This is great. You got all the instruments here that you would in a SST?
As you can see, we don't have a full set of instruments. We have only those that are required for our research purposes. Are you ready in the computing room?
Roger, anytime you're ready.
Here we have the altimeter. As you can see, we're starting out at 1,000 feet. We'll be making our approach at 130 knots.
Oh, so we're not supersonic coming in here. We've slowed down a lot, all right?
This is the final portion of a supersonic flight, and you'll be given a little bit of an idea of how it looks to approach with this large aircraft, and I want you to note in particular the response for this type of a vehicle.
Okay.
If you're ready, we'll go ahead.
Fine. Let's go.
We're now in motion, making our approach at roughly 1,000 feet. We'll be coming down on the glide path now at 500 feet per minute.
Is that the airport there ahead?
The airport's directly ahead. I'll give you a little idea of the maneuver.
Oh,
This vehicle. We'll start over to the left and make an offset correction before we get down to the runway.
I can really feel that. I see what you mean. It does respond very slowly when you
Yeah,
change its
you
control.
remember, this is a very large aircraft,
Right.
and the response of a large aircraft is necessarily slower for safety and structural reasons. We'll actually overshoot the runway and come back, get lined up. You can see we make a correction to go up if we're too low, and go down if we're too high.
Can you make this behave like a delta or a swept wing or any type you want?
Yes, by proper adjustment of the stability parameters, we can simulate any of the supersonic transport configurations.
Now we're getting...
We're now just a little bit above glide path. You can see the runway directly ahead of us.
About 300, less than 300 feet.
This approach is being made under visual conditions, but you can imagine that the entire approach down very close to the ground could be made under instrument conditions.
We're about ready to touch
Now
down.
ready to touch down. There we are on the runway.
I could even feel it touch.
You can notice the
Very
light that
realistic.
comes on to indicate that we're actually on the ground.
Well, that was a very smooth landing.
That's just typical of the many landings that have been made to ensure that the supersonic transport can carry out a mission in a safe and efficient manner.
Well, thank you very much, Mr. Anderson. Once the testing has been completed and the results evaluated, the decision on a specific version of the SST can be made. By 1974, America's supersonic transport should be in the skies. But as progress would have it, this newest of airplanes is already, in a manner of speaking, becoming obsolete. Research is even now underway on the next generation of vehicle, one that feels most comfortable at speeds between 6,000 and 16,000 miles an hour. A thin, rocket-shaped scramjet, the hypersonic plane they call it. No longer seems even improbable that one day, New York to London may be measured in minutes. I'm John Fitch, MIT science reporter.